1-to-1 and onto. So they're at the end we want to apply the ideas to numerical functions, but ultimately the idea has a broader applications with functions of any nature. Okay, so they could be numbers or locations or anything imaginable, starting with those little pictures that we have had of people and balls. Okay, but I still want to concentrate on the most important, and that is the numerical functions. So I want to have as a summary illustrate each these concepts in a little table. So as a summary, so I'm going to put so a table of 4, just 4 cells. So onto, not onto. Okay, and then 1-to-1, not 1-to-1. Okay, it's probably the easiest way to start with this is to actually remember a bunch of basic examples functions that are both 1-to-1 and onto, because they are very regular, nicely behaved. So x cubed would be best. Well, actually any linear function other than horizontal will do. But if you want anything slightly more complex than that, then x cubed is your example. Now let me put x on the list just in case. Okay, so now let's move horizontally from this, and we want a function that is 1-to-1 but not onto. Okay, so it means that the horizontal lines will have only one intersection, but with exceptions. And the exceptions might be only those where there's no intersection. So some lines have one intersections, others have no intersections. These are the only possibilities that we have. As you can see, the one on the left, all the lines will have exactly one intersection. Okay, here the function that, as I said, which is 1-to-1 but not onto, is 1-of-x. 1-of-x, and we'll see more examples later. Okay. Like I said, all horizontal lines will have one intersection with the exception of the x-axis, which will have 0 intersection. Okay, now we're moving down to the second row. Function that is onto but not 1-to-1. So which means that every horizontal line has at least one intersection, but at least once it has more than one. Okay, so so the example that I had was x cubed minus x. So in other words, it's still uncomplicated, really. Just a cubic polynomial, so but not just slightly more complicated than the last one. Goes up, down, and then up again. Because of that down part, that's why it's not 1-to-1. The rest is the same, similar to x cubed, so it still goes to infinity on the left, to the other infinity on the right, but in the middle it makes this little twist or fold, if you prefer, and that's what makes it not 1-to-1. So let me point that out, what makes it not 1-to-1. This one, what makes it not onto, that line has no intersections. And finally, the last example is a function that neither 1-to-1 nor onto. There are a lot of examples of those. And the simplest one probably would be x squared. So it has, well, let me maybe use orange. So it has two intersections here, and then 0 intersections there. Okay, 0, 0, 2, 3. Oops, orange. 2 and 3. Okay, so I'm marking the number of intersections of my my graph. Well, no, my graph with this particular horizontal line. So as you can see, and those pointing out the two ways, two conditions that can be violated. The orange one violates 1-to-1, okay, and a red one violates the onto condition. So once again, the number that accompanies the straight line is the number of intersections with the graph. Okay, so the red one has no intersection with the graph. The orange one has, well, too many, sort of. Okay, so 3 here and 2 there. Okay? So that's a summary of this discussion, even though it will be applicable to, as I mentioned, to other functions as well. Okay. Any questions about this? So the idea, this is meant to be just present an idea of these of what makes functions violate these two restrictions, and you can certainly think how you can have more and more of this kind. So instead of 3 intersections at the bottom left, you can have as many as you like. If you go up and down, there will be more violations, but it doesn't matter. Just one violation means that the function is not onto not 1-to-1. On the other hand, if you look at the second column, just as long as you can squeeze one horizontal line that does not touch the across the the graph, then you have a function that is not onto. And in addition to x1 over x, you can x squared, x squared, x to the 4th, any even power will have the same rough shape, plus the absolute value of x also. Okay. The extreme example of that fits also in the last item, the last cell, is constant function. A constant function has a horizontal line, which means that it certainly does not cover, will violate both of the properties. Okay, so we will be, as we introduce new functions on and on, we will revisit these issues, and every time we ask a question about what is the domain, what is the range, and so on, we'll also be asking always the question of who is it, one-to-one, onto, or one, or both. Okay, so in the meantime, we're moving on to the next topic called compositions. So the problem, I want to start here again. So as you can see, what we're looking at here is 2 sets, x and y. X and y. One has 5 elements, the other one has 4. One reason why it cannot possibly, by the way, when you have 5 here and 4 there, you cannot possibly have a function that is what that is 1-to-1. 5 and 4, which means that at least 2 of them will have to have the same value on the right. So the 2 arrows will have to come together inevitably when you have the mismatch of numbers. But that's not what it's about. So, and then I have a function f here. Okay, so I set this aside. Let me sort of move on to move away from the boys there and concentrate on the balls separately. And I want to just examine the colors of the balls. Okay, so in other words, I'm building a new function. Okay, so how? So first of all, I call the colors. It's a new set, and I call it Z. Okay, so whatever is the 20 colors or so. Okay, and then each ball has a color. So that is my new function, which I will call G. I'm building a new function. by drawing arrows from balls to colors. So the first one is orange. Well, maybe this one. Orange. Okay. Yellow. White is here, and the brown. Maybe this one. I don't see any better match. Okay, I have built a new function. Okay, so like I said, from balls to their colors. That's a new function which exists entirely apart from the function that we just considered. Okay, seemingly, but if we now zoom out, we can actually combine these two functions into one. How? How do we combine them? What would you, looking at this picture, what would be a meaningful question to ask? What does this diagram tell you about what's going on? So there's a correspondence between boys and balls, and then there's a correspondence between balls and colors. What about the correspondence between boys and colors? We just follow the arrows. We just follow the arrows like this. If I start with Tom, and he likes the ball of what color? Orange. Okay. Ben likes same. Okay, and then on and on. Ned likes yellow. So at this point, there is no need to remember about the balls anymore. Well, or at least in a minute. Ken likes, these two like both Sid and Ken like brown. Okay. So one function, the other function combined together. What have we created? We created a new function. Okay, let me try to make that point. Okay, so I'm building a new function from these two. So I am eliminating all the product, the disposable part. So I'm going to dispose of these functions that we already have had. So the first function f is now being eliminated. The second function is also being eliminated because I don't care for it as well. So there's some leftovers. But the function from the balls to the colors is of no need to us. Now I want to go straight from x to z. Okay, so I am eliminating y, as well as eliminating all of these. Okay, I have a new function. It's not f, and it's not g. It's the combination known as the composition. So arrows start at set x and at set z, and that is all it takes for us to have a function. It has exactly one origin for each arrow, and it has exactly one ending for somewhere at the set z. Well, by the way, what kind of function is this? In terms of the classification that we have been talking about, what kind of function is this? In terms of one-to-one onto. Is it 1-to-1, or is it onto both? Neither. Before we move on to talk about composition, so let's classify it quickly. Is it onto? Why is it not 1-to-1 first? Not 1-to-1 because, well, it actually happens twice, right? This is actually also orange. So both of the Ben and Annette end up orange in both Sid and Ken and Ed brown, okay? But it is not onto either. Look at the missing parts. That's what onto is. It covers the whole codomain. So Z is the codomain, and it's not entirely covered. So it's also not onto. Okay. Well, so that's just a nice way to test what we have learned. But our interest is understanding composition, and that's what we have here. Combining two functions into one. When it is arrows, it is fairly straightforward. You just follow from the arrow to arrow. So let me have that picture done one more time. So suppose I have x here, y here, z here. I have a function here that's say f, let's say g. Okay, so I have x with some elements, I have y with some elements, and z with some elements. Okay. So then I draw arrows from the first to the second, maybe onto, maybe not. So that's f. With then entirely separately from this exists g. So like this maybe. Okay. So there are no restrictions on 1-to-1 onto. It doesn't matter. We can combine them in that manner very easily. So once again, let me draw one of those. So say this is one path. Starting here, let's say this is x. Well, x lowercase. Let's make it red. So I start with x over here. I move to y. So y is equal to f capital of x, and then I follow the arrow for the second time towards z, which is g of y. So again, what I have written here are two steps that are unrelated from each other, even though I cannot carry out the second step until I'm done with the first. So I need to know where my x will end up in z. So that's and I have found it, but I have to find first and make a stop at y in order to know where to proceed from there. So it's like you will receive instructions at your halfway destination, and then you'll know your final destination. Okay. So once again, from x to y equal, or if I write it in the opposite order, f of x is equal to y, and then under y, y under g goes to g of y, which is z. Altogether, if I am combining them together, this is what I do. So combining two functions existing separately, f and g, have been combined into one. Like I said, it's called a composition. Let me write it out. If you want to be more formal here, so f from x to y, g from y to z. So given two functions, given their composition, say h from x to z. So y is disposed of, is a function computed in two steps. which I already have here. Y is equal to f of x, number 1, and number 2, z is equal to g of y. Okay, I have to insert it here somehow. So then, if that is how it's computed, then z is equal to h of x. Okay, so that's the formal definition here. But the picture certainly illustrates things straightforward. It is a procedure. Remember, functions are procedures described by possibly a list of commands, and we have a list of commands, right? So what is H now? It is a list of commands. How many commands? 2 commands. Command number 1, execute F. Command step number 2, execute G. So this is the list of commands. So that makes a function. So it's possible that F itself is a list of commands, as well as G itself is a list of commands. And then to combine them together, you just literally put them like one under the other, and you have a new list of commands. Okay. So once again, you can think about computing taxes, and then maybe first half of the operation is how to compute your taxable income, and then the second half is how from the taxable income to derive your tax liability, like that. Okay. So once again, the key is that it is the computation is consecutive. Consecutive computation, so you cannot start the second step until you are done with the first. Okay, so the graphs, so back now to numerical functions. So this is just an illustration starting point. But if we now go to numerical functions, then things become more complicated because we are used to so much to graphs, interpreting functions as graphs, and that doesn't really work out that easily. So if I'm now looking at numerical functions, suppose this is my f, y equal f of x, okay, and then the second function is let's say z equal g of y. You see how things get complicated. Okay, so this is what the numerical function would look like if we match up their what's supposed to match up here in the middle. As you can see in my initial diagram, the what is y? It is the codomain of f, but at the same time it is the domain of g. So that is the matchup. So two functions, I cannot combine them unless I matched up the beginning of the first with the ending of the first with the beginning of the second. Okay, so that works out okay when it is by design that way. But if you have two functions that might have nothing to do with each other, and you try to combine them, numerical functions, then you only have these two graphs. And what do you do with them? It is not that easy because once again, let me try to draw arrows of how you would be computing these functions. This is how you compute from x. You'll find f of x over here using the graph. But then this is the output of f. But then that output of f becomes the input of g. So it has to do this. So input of g. And then you use the graph of g in order to find, so that would be my y. It is this time, it is on the y-axis, but in the on the graph of the other function. So as you can see, that is a complex match of where my y-axis here. Look at it. This is the codomain, the output of the first function. It is the input of the second. So you have to make that trip in order to combine the two functions together and ultimately compute the answer if you're using graphs. Okay, so if you're not using graphs, however, there are better ways to do it, and that is one of the reasons why we spoke of the functions as transformations. Okay, so then we don't worry about graphs anymore. We think about how x is transformed into y through what we've just been talking about, say x, and it is transformed into y, say, I don't know, say stretch, like this. So this is my f, it is a stretch. Okay, and now in this context, combining two functions isn't hard. It's just applying a transformation two in a row. So that's one, suppose it is stretch, and the second one is, suppose it's also stretch. Why not? So stretch by 2, stretch by 3. Say. Okay, so that's my G. So then what has happened, you think about what has happening geometrically with the with that. You start with x, or rubber band, you stretch it by a factor of 3, by a factor of 2, then that already stretched x-axis is stretched one more time by a factor of 3 this time. Okay, so then if I want to produce now my function h, which is between x and z, what kind of function is it? Well, if you stretch once and then stretch twice, what's the end result? It is a stretch, but can you tell me what the factor is? By 6, right. So the distance is doubled, and then they tripled. Altogether, they 6 tuples. 6 tuple. Like this. Okay, so that's an example of what you can, how transformations help to understand what we were talking about. So insert here shifts. So 2 units up, and then 3 units down to operate two transformations that we have. So we 2 units up, and then 3 units down. Altogether, we have a shift by 1 unit down, right, like that. So it is a consecutive applications of transformations, and naturally the end result will be a combined transformation. Stretching, folding, you fold and then you stretch, or you stretch then you fold, and things like that. So you have an object and a piece of wire, and you're doing things with it, or you need a piece of rubber to stretch it. But all of that can be at least understood what we have in mind. When it is literally 2 consecutive transformations carried out in that order. Naturally, in this particular case, the order doesn't matter. If it is by 3, by 2, then by 3, or by 3, then by 2, the result will be the same. But you can think of examples when the order does matter, and that is why we use a notation for a composition that has what? It has, this is the notation. It is G circle F. Let me make a better circle here. That's what my H is. So that circle stands for composition. So it is like, it's as if we introducing one more operation. So we know for algebraic operations on numbers, and you can have those operations on functions too, but this is the operation on function that you cannot have. You cannot do this with numbers. That is a very specific to functions operation. So producing new functions from old, and that's how you do it. Okay, so we set aside transformations. We'll come back to it many times, but one most common way of thinking of functions is as black boxes. So we have diagrams. X, input in F, output Y. Okay, and then over here we have function G, input Y, output Z. Okay, So what do? So they exist so far apart, but then we wire them together, and we just, since we, not by coincidence, we have the y, the same name of the variable, the output of the first, the same as the input of the second. So, which naturally we just plug in the value of y into the second function. Specifically, you can say add 3 is my operation, x, y, and then it comes into the second one, which may be multiplied by 2. Okay, so consecutive operations. So there is no doubt that if you know how to carry out the second and how the first and how the second, then you combine them consecutively, you know how to carry out the whole thing. And to emphasize this idea of, so this is being F, this is being G, this is what the composition sort of, we create a bigger black box. We have 2 black boxes wired together consecutively, and then we might be able to think about it as if there's only one box, and then the input is x, output is z, and y has disappeared. We might not care. Okay, so somehow the computation is carried out, and then we just all we care about the x is the input and z is the output. Okay, so specifically, and then so that part is really not that complicated. We progress from this idea to algebra, and that things slightly become more complicated. But if we just take take this diagram and derive algebra from it, it is not really that complicated, because if I just take the first function, which is what? X at 3 gives me y. So x plus 3 is equal to y. Okay, that is my f. And then this is my g, which says what? Multiply by 2. So I take my y, multiplied by 2, and I get z. So that's the algebraic description of that diagram that we have over there. Okay, so so that is these 2 functions. Now, how do we combine them together to produce the composition? So composition, F circle G. I'm sorry, G circle F. So remember, well, why is it G circle F, not F circle G? It's because we're reading it from, in algebra, we just commonly read things from right to left, even though we draw things from left to right. Okay, so, so how do we carry it out? We know that y is to be substituted, so that part is actually very straightforward. So once y came out of the first function, you just plug it into the second. So what is the meaning of plug in the algebraic context? Substitute. So substitute, and we have indeed, so y is equal to x plus 3, which is what y is replaced with. So substitute or replace, either way, replace y with what it is. So I'll have, not y, but rather I write what? X plus 3 times 2 is equal to z, and that's the whole thing. Right, so now I have a formula for my function. Our computable y is been eliminated. It is a disposable variable, and now I have z directly computed in terms of x. So I could write, if I want to use that notation of mine, this is what I write, like this: G circle f. That is the name of the new function. Okay, so f and g were the names of the old functions. And now I have produced a new one. So this is the key step of substitution. Y here, y there, so why not just replace it? So G circle F is the name of the function. So, and then it's followed by this, as we always write with functions, name of the function followed by the independent variable in parentheses. Right. So that's what we do. And then on the right we have our formula, which I already have: x plus 3 times 2. So the substitution is really fairly straightforward, even though the formulas might be more complex than that. But it is literally a substitution that we did some time ago. So replace the variable with the formula, possibly, or even likely in parentheses. As here, what you don't just replace y with x plus 3, but replace y with x plus 3 in parentheses. So that's my one. So if you do, then there should be no trouble whatsoever. Okay, so let me carry out a little bit more, another example of this kind, just for practice. So let's set aside the diagram, even though probably a good idea to keep it in mind. So let's say find the composition of two functions. Say f of x is equal to x squared minus 1, g of y is equal to square root of y. Okay, so it is as it stands. First of all, they didn't mention the order of things, of computation. So even though the functions are in order, then it is to be assumed that that this one is the first, and this is the second. Sometimes the problems in your homework might be missing some pieces of information, so you have to fill in the blanks. In this particular case, the order of operation does matter. Incidentally, you can see that. Let's take a step back and realize that replacing the order f followed by g, replace it with g followed by f, would produce a different result, right? So first of all, they don't match together as easily as this. But you can imagine that if you rename the variables, you can have operations first multiply by 2, then add 3. Multiply by 2, add 3. What's the formula? So I start with x, multiply by 2, add 3. What do I get? That's right. So as you can see, it's not the same as x plus 3 times 2, right? So this is 2x plus 3, and that one is 2x plus 6. This one is, if you want to simplify, you'll have 2x plus 6. So it's not the same function. The order does matter. Just a note. So then when you have two functions, then you have to determine in which order you're going to be executing them. And so then naturally that you assume that if you're given in that order, then the first one is the first and the second is the second. So then you think as if the first one is the first box and then the second box. And then you also then assume then the formula of the first will be substituted into the second, like this, or like that. So in other words, you assume, even if you're not told that, you assume that the output of the first function will be the input of the second. So if you see the input of the second function is y, then you'd better call the output of the first one y, and then so that you know where everything goes. And then once that's been sorted out, the computation is not hard, but you still have to write out that part, that the left-hand side, to using the proper notation. So it still will be G circle F, okay, to indicate the correct order of X. Okay, and now I take my formula for the second one and plug in the first one into it. Okay, I circled it in green, so it's so what's the answer?
Square root of x squared minus 1.
That's right. Yeah. So and that's the whole thing. So as you can see, it's a function of x, and it is there is no y. That's for sure that you have to eliminate that extra variable. Okay, so it's not really that complicated.
Would there be a different instance where x squared minus 1 would be substituted in the y and x and g?
Into y? No, I replace each y that I see. I replace it with x squared minus 1. Let me. I hope this is what you're talking about. So if I take what I have over there on the right and replace let me take this. So g of y is equal to square root of y. In the meantime, y is equal to x squared minus 1, and y at the same time is also equal to f of x. Okay? So then the substitution can be more explicit than that. If I just replace, if I substitute y here and y there, then what I have is g of f of x is equal to square root of x squared minus 1. Is that what you're talking about? I don't think you were talking about that.
Yes. From and the original picture where you had f of x equals x squared minus 1, where you drew a circle out and you drew two arrows to the two different lines.
Yeah.
I was just wondering if there were different circumstances to substitute for different ones.
If it's the same y, you better replace it with the same thing. So it's like there is one output of the first function, and then it replaces the input of the second. And it just y appears twice on the left and the right as the name of the input variable of g. Okay, so you could literally substitute, replace y with what it is. You can even rename it if you like. But if you have a specific formula, then it appears twice on the left and on the right. I did slightly different at the bottom there, so that I combined the names of f and g on the left, and on the right I did the actual algebra where I literally did the substitution of x squared minus 1, replacing y with that. But this was just the point being that this is an alternative notation for, it's not really much of a notation, but rather it points out the order of substitution of my formula. That's what I'm trying to point out here. So to saying that this is the same thing. Okay, so the meaning of G circle F is what? Is what's in the next line, in the next item is G with its input in parentheses substituted by f of x. Okay, so it's a bit more. Both of them are kind of cumbersome, and that is the algebraic frequently more cumbersome than I think the idea of consecutive computation is really not that complicated if you look at it, in that manner. But the algebra looks with all those parentheses might look intimidating. So it is better to stick to, at least for the time being, to specific functions because what we have here is also not too bad. Just substituting y into x gives you the answer. Okay, the problem that we have solved twice is given two functions, combine them together. Every problem that you face in mathematics has the opposite. So the opposite is you have a function, decompose it into a composition. So opposite problem, decompose. So let's say say my function h of x is 1 over x cubed plus 1. Okay, so there is nothing really wrong with this function. You can compute it as it stands. There's no problem really, but you are asked to break it into smaller pieces if possible. It is possible to make it to carry it out in two consecutive steps. So that's what decomposition is. So the idea is represent h as the composition of, say, f and g. Okay, exactly. The end result should be the same what we started with in the previous example. So it should be like this. In order f, g, x, y. So this is my h. This is my h. Okay, and I have to, and it is given to you as a black box with the formula, and then you sort of have to look inside and show its workings. Okay, and ideally it's just carried out in two steps. By the way, probably to keep it myself consistent, I will put the output variable z for h. So then I introduce the intermediate variable, I'll call it y, inside. Okay, so that's the idea. You could go straight to algebra, or you can think about it for a moment. So how would you, can you see a two-step procedure for computing this function? Without algebra, without anything. 1 over x cubed plus 1. How about I delete plus 1? 2 steps, what do we do? I mean, it's a simple function, 1 over x cubed. How would you compute it to begin with? I give you 3. What do you do with it? I give you 3. How do you compute the function?
First is to find a substitute for y.
No, you're looking too far ahead. Just answer the question. So I'm giving you 3. How do you compute the h of 3? Right. Okay. And then what? So if the substitute is not actual computation, what's the first step you're going to do? You're going to cube it. You're going to cube it, and then what? X is given, say 3. I will cube it first, which is giving me 27, and I take the reciprocal of it. These are the 2 steps. Okay, so these are the two operations that I face here. Cube it, and then take reciprocal. So in the previous example, it was like add 3, square it, or multiply by 3, square root of it, take square root of it, something like that. So you can always describe it as just a list of steps, or a diagram of consecutive steps. Either way, these are algebraic steps. It is without doing any extra algebra. You cannot really carry out the 1 over x cubed in one step. You know, unless there is a. You should think about buttons on your calculator. Okay, so you are pushing the. You cannot compute 1 over x cubed by pushing only one button, unless there is a function that's specifically designed to do this particular problem, which is not the case. Okay, so you would have to push a cube first and then the reciprocal second. So these are the 2 steps. Okay, so we'll continue with this. I'll assign homework later today.